Okay, let's wait a few more minutes because I see that the people are joining the call now. Okay, so we'll wait until we have 50 participants. Okay, maybe not 50, but let's wait just 2 more minutes before we start our lecture. The note, so the slides are already on Campus Wire. If you go to the lecture slides post, which is pinned, I already uploaded the lecture slides for this one. So you should be able to check that. So yeah, Campus Wire is online back again. So please do use Campus Wire chat rooms to ask questions. And even if we don't answer it right away, we'll be able to check the questions later and then leave the answers, and then you can check it later again yourself. Right? All right, so let's continue. So we only have 45 minutes this time, but we also have a slightly smaller amount of contents this time. And then this is going to be more or less about trying to give you some sense of what the different approaches to language modeling. What we have learned so far is that if we know how to do language modeling, then we can build question answering system, which you're going to see later. We can build machine translation system, and we can even build neural conversation model. But then you start wonder, is the autoregressive language model the only way to go about? Maybe there are different ways to build a language model. And then once we have different ways to build language models, what it implies is that we are going to have different ways to build machine translation as well as conversation models. So it's a very interesting perspective that we can have. So we've been thinking about the language modeling as trying to look at what has been generated so far, all the previous tokens, and then build a classifier, text classifier that's going to predict what the next token is going to be. And then once we have that, we can simply multiply all those conditional probabilities of the next tokens to get the score or the log probability of the entire sequence. Or of course, we can do the summation of all the log probabilities, right? So instead, we're going to look at two different approaches here. Let's see. So for the one that we're going to use is BERT. So how many of you have heard about BERT? Not the BERT the Muppet, but BERT the language model that was released by Google. If you have heard about BERT before, please press yes or say yes on the chat, please. Oh, okay. So quite a lot of you have already heard about BERT. And then there is, of course, not everyone has heard about it, but some people heard about BERT. Okay, that's good. So what BERT is a so-called masked language model that was released a year and a half ago by the team in Google Brain in Seattle, led by the Jacob Devlin. And then what it is to build a very large transformer-based language model that is not autoregressive. So the BERT tries to build BERT is a language model that is not autoregressive and is based on transformers that we learned yesterday. And then we're going to look at it today later in the last lab session as well. And then BERT turned out to be an amazing way to pre-train or initialize the parameters of the text classifier. Once we use BERT to pre-train or initialize the text classifier's parameters, even with a very small amount of data, we can train a text classifier to do as well as humans can do on many simple text classification problems. So that was a kind of revolutionary finding from the in the natural language processing field of natural language processing during the past 2 years or a year and a half. So a lot of people have been talking about BERT as a way to initialize a good classifier. And then that's actually true. So these are the two benchmark leaderboards. So one is from the glue, and then the other one is from so-called super glue. And then these two benchmark or the suites of benchmark tasks were released by the people at New York University here at NYU. And then these have become de facto standards in benchmarks for evaluating text classifiers or the neural net-based text classification modules or the question answering modules. And then as you can see, in the case of glue, which is an older one, every, let's say, top rankers use something with a BERT. So the first ranker uses Albert, which is a slight variance of the original BERT. The second ranker or third ranker uses Roberta, which is another variant of BERT. Fourth one also Roberta, which is the variant of the BERT. XLNet, which could also be considered as a bit of a variance of the BERT, and then on and on and on. And then these are actually all better than human baselines. So when we ask the untrained humans to solve these problems, they are just solving as well as these BERT-based models. On superglue, which is a bit more recent and has larger data sets and the more complicated benchmarks, still the humans are better, but generally saying, BERT is there, BERT is there, BERT is there, BERT is there. So you see that the BERT has really revolutionized natural language processing, at least in the natural language understanding or text classification, by initializing the classifiers amazingly well. All good. And let's think about what BERT was trained to do. So BERT learns a distribution. And then what it means by distribution is that it is a language model, right? So in our case, throughout this week, what we have learned is that the language model is to learn a distribution over all possible sentences or natural language texts. So the fact that the BERT learns a distribution means that BERT is a language model. However, how it learns is a bit peculiar. Let's assume, so we're going to always look at the conditional language model. Although usual language model is just conditional language model without having any source sentence or the empty source sentence, so it's all the same thing. Let's assume that there exists some ground truth distribution. So this is the ground truth distribution. But of course, ground truth distribution, we don't have any access to. We're going to just imagine that there exists a ground truth distribution underlying natural language text. Makes sense, right? We don't have access to it, but we can guess that that exists. And then what we want to do is we want to train BERT here. How will we do that? What BERT does is to try to take as input a small number of observed words. So given a sentence, BERT is going to mask out a lot of the words. So it's going to mask out some of these words, and then we're going to only be left with some of the words in the sentence. So we are corrupting the source sentence or the sentence so that some of them are masked out. BERT cannot see some of those words. And then that's going to go into BERT as the input. And then what BERT needs to do is to try to recover what those masked out words are. So what it computes is that the conditional distribution over those missing or masked out words given the observed or unmasked out words. And then, of course, we know exactly what this distribution should be in ground. We know what the ground truth conditional distribution should be because corruption, we corrupt the sentences ourselves, right? And then what we are trying to do is trying to see the difference between the ground truth, that is the actual words that were masked out, And then we try to match that with the whatever has been predicted by Pert. So what Pert does is to look at a sentence that is corrupted. And then when we say corrupted, what we mean is that some of the words in this sentence are randomly masked out. And then what this Pert needs to do is trying to figure out what those masked out words are. And then we train this Pert to predict those masked out, masked out words as well as possible by minimizing this divergence. And what it means is that because Pert learns a distribution, that is, Pert is a language model, we should start asking ourselves whether we can generate directly from this model. And then there's a weird thing going on here is that let's think about it in this way. In autoregressive language model, we knew how to generate it quite reasonably well from the very beginning because we knew that we knew what is the order of generation should be. What do I mean by that? So we knew that in autoregressive generation, we want to generate the first word first because first word does not depend on anything else. And then given the first word, we wanted to generate the second word because we know that the second word depends on the first word. And then once the first two words are generated, we want to generate the third words. And then because that one is dependent on the first two words, and then we go on and on and on. But in the case of Pert, because we randomly masked out the words in the sentence during training, there is no particular order in which the masking happens. And then there's no particular order in which the Pert is good at predicting or filling in those mask points. In other words, we need to figure out not only what words needs to be selected or which words needs to be selected from the vocabulary at each time step, but we need to figure out which location or which position needs to be filled in. That is, we need to now search for a directed acyclic graph over the sentence. And if you think about it, there are many different ways in which we can build a graph. One particular way is the autoregressive way. And then this is exactly the paradigm that we use in order to build a language model so far, right? So every word at time step t is going to only depend on the previous words. On the other hand, it doesn't have to be like that. Maybe what we want is a graph like this. That is a disconnected graph. So the second word depends on the first word, but the third word doesn't depend on the first two words, and then the fourth word depends on the third word. Or maybe something more less trivial. Right? Let me just erase this. What do I mean by less trivial is that maybe the first word and second word can be predicted independently from each other without being dependent on anything else. However, the third word needs to depend on the first word, and then the fourth word depends on everything else. Maybe that's fine. Or maybe something else. In other words, we need to figure out what is the right way to generate these words in a sense that we need to decide on the order of generation as well. And then this was pointed out recently by David McAllister, who is a professor at the Toyota Institute in Chicago as well. So what it means is that we can think about some kind of generalized framework of sequence generation that generalizes autoregressive modeling or the autoregressive generation or the autoregressive language model that we talked about by deciding also what to generate, in which order to generate what. So far what we have learned is what to generate. We focus on what to generate because we knew which variable, which order in which the things need to be generated. Left to right or right to left, just one monotonic order. But now what we are saying is with this kind of Pert-like model or masked language model, what some people call it, masked language model. With this masked language model, we need to decide which order things are going to be generated as well. And then this whole procedure can be written down as alternating between first determining the next set of variables to replace, and then given that given the determined set of variables, we decide which words should go in. Does that make sense? Yes. So that is, we start from all empty sequence, and then first we're going to decide which word we're going to fill in. And then in this case, our model selected that the second word needs to be filled up, and then we now use Pert. So Pert is going to take as the input entire thing with the indication saying that the second word needs to be filled up. And then Pert is going to try to fill up the second word. And then now given the second word filled up, so this is empty, 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 but the second word, we know what the word should be. We're going to again decide which next word should be filled in. And then that one is going to be this time the fourth word. And then given the fourth word needs to be filled in, and all this empty, filled in, empty, empty sequence, Pert is now going to fill in the fourth word. Now you see the pattern here. We go back and then trying to figure out which next word needs to be filled up, and then it actually decides that the first word needs to be filled up, and then given empty, second word, empty, fourth word, where the second and the fourth words were already selected or filled in by Pert, we're going to let the Pert fill in the first one. And then now, given this, we're going to decide which one we're going to mask out again. And then we have only one words to fill in after all, so this is automatic. And then now Pert is going to finally fill in the third one, and then we end up with the completed sequence. Now, if it were autoregressive model with the monotonic order as before, then we would fill it up in an order that is, we fill up the first one, we fill up the second one, we fill up the third one, we fill up the fourth one. However, in this case, because we are going to use Pert, we can actually be very, very flexible about in which order the words are filled up. And in this particular example, the words are filled up in an order that is second one first, fourth one, first one, and then third one. And then the question is, how do we decide this order, right? It turned out that we can rewrite the whole thing as an autoregressive language model again. However, we now do the language modeling not only on the words, but also on the location. So we need to do the autoregressive model on the location as well as the words. So the words are X, so that is the partially completed sequence. So, and then Z tells us what has been generated, which order in which the things have been generated so far, and then what should be the next location at which the next word should be filled in. And then the equation, this kind of formulation looks complicated, but if you look at it more carefully, what it's saying is that let's look at the second one first. Given what has been completed so far, so what has been generated so far, and then which locations those generations happen, and the source sentence, if I knew which location should be, then I'm going to replace that location with the prediction from Pert. Now, on the other hand, given what has been generated so far, and then given in which order, now I need to decide, I need to have another network or the neural net that tells me for each location whether I'm going to fill it up now or not. And then you alternate between these two steps. And then that is precisely what we saw here, right? So we're trying to predict what should be which location should be filled in. We fill it in. We're trying to check which location should be filled in again. We fill it in. And then we go on and on until everything is filled up, and then we have a full sentence. What it means is that the generation from Pert corresponds to trying to detect the dependencies. And then this is really interesting in a sense that in autoregressive model, we decided which variables or which location should depend on which other locations. There was every word in every location depends on all the words from previous steps. We decided. But now with the birth and generation from birth, we are asking the model or our algorithm, machine learning algorithm, to figure the dependency out. That's pretty awesome, in fact, if you tell me about it, because one thing that has been always been very, very difficult in machine learning is to learn from data the dependency patterns among the random variables. It turned out when we have enough data, we can actually automatically detect it and then use that information to generate from these kind of models. Yeah, these are all from my actual own work together with the Sean Welleck, who is here. And then also Fu Meng Hood, another course assistant, has been working on this quite extensively. And then I'm hoping that the Sirius, the last, let's say, course assistant who was here last year as well, is going to also look into this kind of structured prediction as well. He's been looking more into the computer vision application, but you know, we are getting there. I think I can convince him toward this direction, yes. But anyway, so we actually did some experiments here. And then so what we need is that we need to actually have this distribution model. But then, you know, what is the right way to model it? We simply made a log linear model, which you may have learned with the different names. Logistic regression, or you know, the softmax classification, log linear models, maximum entropy models, all these things are the same thing. And then in this particular paper, Sean Welleck, Elman Mansimov, Alex Wang, so all those three are PhD students at NYU, and together with them, we just made a log linear model with the manually crafted features and coefficients in order to kind of control what can be generated. Of course, we have a more advanced version by Sean Welleck on how to learn entire thing using the reinforcement learning. But unfortunately, we don't have time for that. But since you learned about the reinforcement learning from Benji already, if I remember correctly, so you should be able to kind of guess what we mean by it. Because selecting the order in which the things are generated is exactly what the policy gradient or the reinforcement learning is good at. Right? So then once you do this, you can do the beam search with BERT using this kind of coordinate selection procedure. And then what we see is that for each sentence, the order of generation changes. So we can build a coordinate selection distribution that makes the BERT predict easier one first. Then what we see is that for many of the sentences, the generation is going from right to left. Some of the sentences, it goes from left to right generally, but some sentences, it just goes from the outside to the inside. And then this happens, we can control this kind of behavior however we want by either creating the coordinate selection strategies ourselves or letting policy gradient algorithms to decide how to generate the, decide on the order of generation in order to maximize an arbitrary reward function we can design. So before we move on, let's answer one question by Ariel. What is the intuition behind the optimization problem? How do you model this problem going from the architecture and the generation from BERT? Is the intuition coming from cross entropy? If yes, how? No, intuition does not come from the cross entropy. The intuition comes from the fact that the BERT, so let's, oops. Okay. So intuition comes from the fact that the BERT is learning this conditional distribution. So how we are training BERT is to be able to compute this conditional distribution as well as possible. Then the question is, when we have access to all those conditional distributions, there are a lot of these conditional distributions, in fact, exponential number of them, right? What is the right way to use these conditional distributions to generate a sequence from BERT? And then what that corresponds to is to trying to figure out what is the right directed acyclic graph be underlying this sequence. Because if you think about it, let's take example this second one. And then any arrow here defines a conditional distribution. And BERT is supposed to compute those conditional distributions. So what it means is that once we decide on this directed acyclic graph, then we can use BERT to compute all these conditional distributions and then sample from this distribution accordingly. And this animation is showing the procedure one step at a time. We're going to select what is this dependency or the conditional distribution BERT needs to compute. And then from that distribution, we sample the next word. And then given that, we're going to select what is the next conditional distribution BERT needs to compute. And then we're going to sample from it. And then given these two, now we're going to decide what should be the yet next conditional distribution BERT needs to compute. And then we sample from it. And then given all three of these, now we're going to sample from the final one, final conditional distribution computed by BERT. So it's not really about the intuition, but it's more about realizing what BERT computes, that is the conditional distributions, and then figuring out mathematically what is the right way to generate from this set of conditional distributions that are being computed by BERT. So let's take a look at one example. So you can build a BERT-based machine translation system or cross-lingual masked language model. So I'm going to write it down. Cross-lingual masked language model. And then this cross-lingual masked language model serves as a machine translation system. And then in that case, what we do is we're going to put on one side a source sentence and then fix it while BERT is computing the conditional distributions on the target side. So the source language was German in this case, and then the target was English. So source is given and fixed, source is fixed throughout the generation. And then we start with the all empty translation. And then what our model does is to first figure out which words should be filled in. And then it figured out that, okay, the last word needs to be filled in. And then we use this cross-lingual masked language model or the cross-lingual BERT to fill in that one. And then what BERT told us is that it should be period. And then once period and the source sentence is given, our model or the coordinate selection told us that we need to fill in the third word from the right. And then we asked the cross-lingual BERT, okay, what should the word be? And then this BERT told us that it should be cannot. And then given that, we can continue. So our coordinate selection told us that the fourth words from the right should be filled in. And our cross-lingual BERT told us that it should be democracy. And then we continue on and on. So it started to fill up from the right side, but it jumps to the earlier side and it jumps back to the end. And then the beginning and the middle, and then eventually it filled up everything. And then this is in fact a very reasonable translation of the source sentence. There is a question of how we determine the length of the initial empty translation. That's a very good question. What we did ourselves was to simply build a text classifier that's going to look at the source sentence and then trying to predict what the length should be. And then that one actually works pretty well. Of course, there are many possible lengths that can work with the one source sentence because there could be many different translations. Then what you can do is you can actually do the beam search like that. So you select the top K possible length, you try each one of them, and then you eventually pick the one with the higher score under your model. So if you look at some of the results, you do see that this kind of generation from the undirected or the masked sequence models works almost as well as the autoregressive model. This is what we have learned. This is a state-of-the-art system. And then depending on what kind of coordinate selection or the strategies for selecting the order you choose, the difference is actually pretty large across them. So you need to really learn to do that really well. And then this learned model, this is using a policy gradient, or the reinforcement learning works almost optimally. And then it does not require us to choose the order ourselves. And then because it's a masked language model, we can do something called constant time machine translation. We learn that in the case of the autoregressive model, when we use greedy decoding or beam search, let's say autoregressive model. So our baseline autoregressive model always takes the linear time at least to generate it, because you gotta generate all those, let's say, words sequentially, one at a time. But assuming that we have enough parallel computation with this kind of masked language model and the automatic determination of the location, we can actually achieve a constant time translation. That is, we're going to decide on the budget. So let's say here, we say that, so here, let's just change that. We're going to say that we are going to allow 10 steps. So we're going to allow our BERT to be queried 10 times for the words. And then what happens is we can reveal, or we can decide to fill in multiple words at a time. How is that even possible, right? So let's go back a few slides back. Go back a few slides, and then let's look here. If our selection of the generation order were the second one again, then what it says is that we can generate the first and third word simultaneously because they don't depend on each other. And then we can also generate the second and fourth words simultaneously because they don't depend on each other, given the first and third words. And then we get a similar thing in the case of the third one as well. We can generate the first and second word simultaneously, but then the third and the fourth words needs to be generated sequentially. So this is how we're going to achieve this constant time translation. And then surprisingly, this constant time translation actually works reasonably well. And then we get a high enough BLEU scores. So, and then there has been a number of different work in trying to do the sequence generation or the language modeling with an adaptive order. That is, the order is not fixed, left to right, right to left, but it is determined on the fly as we generate. So the BERT generation, not only the work by Sean and me, but also there has been work from the Facebook AI research, as well as another one from, I think, from Germany. And then there's been another set of work on the learned order generation. One of the pioneering work was done early last year, so in 2019 by Sean, who is our course assistant here as well. So before we finish this, we have about 12 minutes. I'm going to go quickly for yet another paradigm that is a Latin variable model. So this is what we have looked at so far. That is the autoregressive model. That is, the probability of a sequence is factorized into the product of the probability of conditional probabilities. However, yet another way to do so is that we can introduce a Latin variables. You must have learned about Latin variables in the earlier courses that I'm in, Latin variables, and then marginalize out Latin variables in order to get a complicated distribution over the sequence. And in particular, what we do is we build a model so that given the configuration of the Latin variables, so these are the Latin variables here, so there's Z and then X. Given this Latin variable configuration, all these words in the sequences are independent from each other. And then that makes it extremely efficient when we have a good parallel computation, because once the Z configuration is given, we can generate from all these words in parallel simultaneously. We don't have to do the sequential computation. But then because we're going to marginalize out Z, so we're going to consider every possible Z configuration, eventually the full distribution, so that is X after marginalizing out Z, under this distribution, they are not independent. So in other words, we can capture all the complicated dependencies among the output variables once we marginalize CI. So this is a very different paradigm from the autoregressive model where we were trying to determine what are the dependencies directly. So does the third word depend on the first word? Does the second word depend on anything else? We had to determine it very explicitly, but in this latent variable model, what we do is we let this C, the latent variable, to implicitly capture all these dependencies automatically on its own. It's really difficult to fit these latent variable models. In fact, my entire PhD dissertation was on doing so unsuccessfully. However, in 2015 and 14, there was something called variation autoencoders, which I believe you have already learned. And then in variation autoencoders, we don't have time to go into detail. What we do is, instead of trying to compute this marginal probability directly, we're going to compute the lower bound to that. Now, computing a lower bound is always useful when we try to maximize something. So what was the goal of our learning, or what was the goal of language modeling? Was to maximize the log probability of the correct sequence. And in particular, with the latent variable models, we want to maximize the log marginal probability of the correct sequence, but computing this marginalization is very, very difficult. So instead, what we do is we try to maximize the lower bound to this log marginal probability. And then the lower bound turned out to be more readily computable using a stochastic approximation. And then that was proposed by Dirk Kingma and Max Welling, as well as the Danilo Rosende at Google DeepMind in 2013 and 2014. So it has been used for natural language processing earlier, but none of them were that successful. Because learning is easy, because we can maximize the lower bound, but it turned out that generation is not necessarily so, because generation is, as we know already, because we learned it just today, is to solve this argmax problem, and in this case, over the lower bound. So we need to find the sequence that maximizes this lower bound, but maximizing this lower bound is not that easy. And a lot of people have made a mistake in this direction. So instead, what we did, actually, this is work by this is not rejected anymore. This is a paper from 2020. This was done by my PhD students, Raphael Xu and Jason Lee at NYU together with me. And then this is called deterministic inference algorithm. So we introduced a notion of the delta posterior, and then trying to maximize the lower bound approximately in a deterministic way by finding one solution, one local solution that maximizes it. And this is similar to a gradient descent or any kind of expectation maximization algorithm that finds the local minimum or the local maximum. And it works amazingly well. And then let's see more in using an animation. Yes, it is it looks complicated. In reality, it's not complicated at all. Only if I had 2 more days to teach you everything, I'll be able to go through all the details and steps one step at a time. You'll notice that it's very simple, but unfortunately, due to the time, and this is more of the less mainstream approach, so I can't really go into the details, but you can just trust me that this is an alternative, a very attractive alternative to what we have learned so far throughout this course. And then this alternating optimization procedure can be thought of as so let's contrast with the beam search. In beam search, we worked in the discrete sequence space directly. So we never actually moved to another space. We were doing search within this space. However, with this latent variable model, what we do is that we start from this continuous latent space, and then we project it to discrete space, and then given that projected version, we come back to the continuous latent space, we project it back, and go back and forth between these two until the whole thing converges. So what it means is that with these latent variables, we're effectively augmenting this discrete sequence space with a continuous latent space. And then this actually helps us solving this optimization problem or the search problem much more efficiently and effectively, because small changes in this continuous latent space could lead to a large jumps in this discrete sequence space. And then what we proposed earlier, what I showed you in the previous slide is precisely a, well, it's not like D, but the A method procedure by which we can solve this problem. So the discrete space looks really, really complicated, but it's just a set of all possible sequences. And then, as you can see, so here are some of the examples. These latent variables or the continuous space allows this generation procedure to make jump. So for instance, in the case of a third example, let's look at the third example. The initial guess has weird sentence parts like the micro manipulation and whatnot. This is going from Japanese to English. So this is Japanese, the English transcription of the Romanization of Japanese. And then we go from the initial guess, and then after running this for about 3 steps, we suddenly have this very big chunk of the phrase appearing in the middle of the sentence. That is, and it has been developed. And this kind of jump is really, really difficult with a beam search, because beam search only makes 1-step changes at a time. So you cannot really suddenly put the gigantic phrase in the middle. And then this is reflected in the BLUE score, as we know, the automated metric to evaluate the machine translation system as well. If we don't run this inference or the iterative step, then the BLUE score we'll get is around, let's say, 24. However, as soon as we run this kind of iterative refinement, just few steps, it jumps by more than 1 BLUE score, all the way up to 25.5 or 26. What it means is that this latent variable model that I just told you about is indeed unattractive alternative to the autoregressive model we talked about throughout this week. So if you want to look into more advanced, let's say, approaches to the sequence generation models, this latent variable model is one really nice way to look into. And then it also allows us to have a better quality efficiency trade-off, because the speed at which the sentences can be translated is much faster, because this approach can exploit this parallel computation much better than the autoregressive models. In terms of the BLUE score, these latent variable models are slightly worse, but in terms of the decoding speed, this is much faster. So we actually ran out of time. So today we learned about, not today, but in this second lecture, we learned about the mask language model and then how mask language model can be used for generation in addition to initializing a text classifier. And also we learned about the latent variable machine translation system or the sequence model that can be an alternative, very different approach to doing the language model. And then in general, so this is the last lecture of this course. We have 2 more lab sessions. We have one special seminar by Sean Welleck later. And tomorrow we're going to have a QA, so during which all 4 of us are going to be present on Zoom, and then you can ask questions. But let's just go over what we have learned. We started on Monday with a recap of the supervised learning, and then there we learned about what it means to build a neural network, and then we learned about what it means to train this network with the always stopping, and then we talked about what is the right way to do the evaluation. It's really important to remember we always have to have 3 data sets: training, validation, and test sets, and that they should not overlap, and you should not look at the test accuracy to change anything in your model. It has to be based on the validation accuracy. And then we move on to the language model, and then we talk a bit about how language model is self-supervised learning, and then we can use a supervised neural network to solve this problem of the language model. And then for the historical reason, we looked at the count-based N-gram language model, which told us, or which helped us identify 2 major issues with the count-based language model. That is that it does not generalize, and also it cannot capture the long-term dependency. And in order to address those issues, we ended up with a recurrent language model that looks at entire history and also uses a continuous vector representation to capture all those similarities, and then is capable of the generalization. And on Tuesday, we looked more into the recurrent neural network and then the peculiarities of training these recurrent neural networks, which led us to investigate or to develop a new techniques such as adaptive shortcut connections, which led to the gated recurrent units as well as long short-term memory units. And then how we talked about how that actually connects to residual networks. And once we did that, we move on to how we can use those recurrent nets to build a machine translation system. And then which was followed by how we can go from the gated recurrent units to attention mechanism that has become de facto standard in building these very deep state-of-the-art machine translation systems such as transformers. And in the lab session, we looked at how machine translation system can actually be built and used. And today in the morning, we learned about how the machine translation can be turned into conversation model, and then how we can build a neural conversation model. And under that framework, we looked into the different decoding algorithms for the autoregressive models. And just now, we talked about how to build the masked language model, and then also the latent variable machine translation systems, both of which are non-conventional approaches, but may be a very attractive alternative for the future research or the development directions. And later today, we're going to have the 2 lab sessions at which we're going to learn how to build these conversation models and use masked language models, not only for generation, but also to see how to make a very simple factoidal question answering system as well. And tomorrow we'll have a QA. You are going to have the final exam. The final exam is going to be online. That is going to be open from tomorrow on the Grayscope. You have access to Grayscope. If you don't have it, you should leave the message on Campus Wire as soon as possible with your email and full name. And then that is going to be open until next week. You need to submit it by next week, Thursday, and then we're going to grade them and release your letter grade a week after. So that's it from me for lectures. So let me just look at the schedule once more to ensure that I know what I talked about. I may not have made all the correct say thing. So we're going to have a break of half an hour, and then we are going to come back at 3:30 p.m. in Kigali, 1:30 p.m. in Accra, and 9:30 a.m. in New York City for the lab session by Shreyas on decoding algorithms. And then we are all going to be online. Please ask the questions on Campus Wire. We'll try to answer. And then after that, we're going to have another break before the remote seminar. All right. I'll talk to you then later then. All right. Have a nice break, and then see you soon.